region of the boundary, which I'll call A now, then there was some subregion of the bulk in here, which we called the causal wedge, where we saw that for operators inside of this causal wedge, they had a representation in the boundary CFT living just in the subregion A. And so we related that to this general problem in holography of how we think about locality in the radial direction. Right? Holography somehow says that if you have an operator sitting in the center of the bulk, then radial locality suggests that you should think of it as commuting with operators near the boundary on this time slice, since in the bulk they're space-like separated. But then we saw that there was some tension between that idea and the idea of the locality of the CFT. So in the CFT, commuting with all the local operators at fixed time is a very strong restriction on operators. And at least according to this time slice axiom, it means that in fact the operator has to be trivial, and certainly at least it has to be topological. So that was a problem that holography needs to solve. And we saw that we also saw that with this subregion duality, right? So that we saw that was related to this radial commutativity, because, for example, if I wanted this to see that this operator commuted with that one, right? Then I could take a subregion like this, and then this guy is in the causal wedge of A, and so then it's going to commute in the CFT with whatever is here. And we also saw.
I'm sorry, just remind me what that line is in the first diagram. That is.
This?
Yeah.
Oh, how is it chosen? So in the vacuum, this is the geodesic that ends on these 2 points. In the causal wedge, the idea was we take the boundary domain of dependence of A, and then we take the intersection of its future and past in the bulk, and this is just the rim of that wedge. Yeah.
Okay.
That's the general definition of the causal wedge. Yeah. So finally we saw this. We had this funny situation where we had operators, so we have regions A, B, and C, whose causal wedges are like that. And then we saw that this operator in the center could be represented on any 2 of these boundary regions, but not on any one. And that also is a little bit surprising from the point of view of locality in the CFT, where you would think that where the support of an operator is should be an unambiguous thing in a quantum field theory. It's either it does or it doesn't act trivially on a region.
So sorry, Daniel.
Yeah.
That diagram, the bulk region, not the last one, but just I'm still trying to understand the first one.
Yeah.
How they explained it. The bulk region within that line is reconstructed by the operators on the boundary A, right?
Yeah. So operators in here could be represented. Yeah. Operators here cannot be represented there. Yeah. Sorry. I did 2 things in the diagram. So.
That's fine. Yeah. I'm with you.
Yeah, that's right. Okay. So here we had this funny thing where the operator was an A, B, or BC, or AC, but not in A, B, or C, and that was surprising because if an operator is usually you would say if you can represent an operator, if an operator has a representation on both A, B, and BC, then really it's just an operator of B, right? That if the support of the operator is well defined, then that's the only conclusion that you can come to. But here we know that B isn't good enough, right? Because the causal wedge of B doesn't contain this. So somehow this operator can't really secretly be on B.
This part I'm not understanding.
Yeah.
Suppose we have 3 Hilbert spaces. The Hilbert spaces for A, B, and C. Then you can have operators that have off-diagonal matrix elements that are just off-diagonal in all 3 places.
Well, let's be clear. So the Hilbert space is a tensor product of A times HB, tensor HC.
Right.
Okay. And when I say the operator is just on AB, I mean that it accesses the identity on C.
It accesses the identity. Oh.
Yeah. So that it's of the form OAB tensor identity on C. That's what I mean by an operator having support only here.
Got it. Thank you.
Well, you might come to this later, perhaps, but one thing is for gauge theory, at least, it's not such a simple tensor product composition.
Yeah, that's true. We're going to discuss a lot about that at the end, but for now, right. But yeah, maybe for this lecture, let's not worry about that, and then that'll come up in the last lecture. Okay. So all right. So there. Right. So AdS CFT has these surprises. I mean, these properties all. Remember, we derive these from the bulk, right? We were looking at properties of the wave equation in the bulk, and we found, commutativity, right? That's obvious because we're simulating bulk effective field theory, and then this amounts to doing Bogoliubov transformations to represent the operator in different ways. But from the CFT point of view, at least to me initially, these were surprising. I mean, by now they're not, because I've given this talk for 2 years, but when I started, they were surprising. So what I'm going to do today is try and convince you that these are really natural. These properties are very natural from the point of view of quantum error correction, and so that if you understand that you should think about the CFT as being a quantum error correcting code, then these now, instead of being surprising, will be sort of almost obvious. They'll sort of they'll be very natural things for the CFT to do. All right. So let me erase this because this was just review, and now we'll start with the next lecture. All right. So quantum error correction, and I'll start by just telling you a few things about quantum error correction. Give you an example. So now do a detour into information theory for a little bit. So quantum error correction is an idea that was invented by people who are thinking about, building quantum computers. If you had a quantum computer, what would you do with it? And one of the basic problems with quantum computing is that it's very hard to preserve the coherence of the memory. Because the memory is not an isolated physical system, and it can't be because you want to do logical operations on it as part of doing your computation. But then the system will be at some finite temperature, and it'll be coupled to the environment, and so it'll want to decohere. So quantum error correction is a procedure for preserving the quantum coherence of the memory over timescales that are long enough to do the logical steps and the logical operations that you need to do to actually do a quantum computation. So the basic idea with quantum error correction, or even with classical error correction, is that you want to redundantly encode the state of the memory into a larger number of physical qubits, or bits if it's classical, than the number of logical bits that the memory is containing. So if you want to store 10 bits of information, maybe you make the memory out of 30 bits of information, and then you try and encode redundantly so that if you lose a few here and there, it's not so bad. So classically, there's an obvious algorithm, right? So say I wanted to send you the bit I. So the idea is instead of sending you the bit I send you a sequence of bits I. Okay, maybe 8 I's. And now, okay, so say the probability of any particular bit being hit by an error is 10%. Then the odds that you're going to hit 4 of these guys is 10 to minus 4, assuming that the errors act independently on the separate bits. Which, from a physical point of view, is kind of a natural thing to assume, right? Because we think the interaction with the Hamiltonian is local. So there's some each different point. We can think of these as being at different points in space. So there's some chance that any one of them be corrupted. So this is called the repetition code. It's sort of the simplest classical error correcting code, and it's pretty good. In this case where it's a 10% chance error, it's unlikely that we're going to get confused if we do this. Quantum mechanically, however, this scheme can't possibly work because in quantum mechanics there's a no-cloning theorem. So you're not going to have a machine where we give you a state, right? right? So now, right, a quantum computer, the memory is made out of qubits, so it's a state of memory is some quantum state. And then, and as with any computation, you want the rules to work sort of independent of which input you put in, right? So then if you want to, to preserve coherence, to do this, right, you want to do something like that, but we're clearly not going to be able to do that. So this is why actually people at first thought that quantum error correction would be impossible. They thought, oh, quantum information is more difficult to preserve than classical information. And so there were skeptics who said we'd never build a quantum computer because of this.
Just to understand that
Yeah.
a little bit, and not to take you away.
Yeah.
I mean, if you could measure psi, then of course you could replicate it. Like if I knew psi was the eigenstate along sigma x, of course I could replicate. But is it that measuring in general psi will be some state in the Hilbert space, and as the computation evolves, it will change or whatever?
Yeah, so in general,
So you don't want to measure.
well, to measure a state isn't something you can do with one copy of the state, right? Measuring is a sort of nonlinear operation where you're given many copies of the state, and then you do many, then you do a bunch of experiments to build up statistics, and then you sort of infer what the original state was. But yeah, in quantum information theory, it's important. The idea is that by quantum information you mean the same thing here. You have an envelope and you have a state in it, and then you want it just given the one copy of the state, transfer it from here to there, or move it from this state to that state, by doing some unitary transformation or something. So just measuring it isn't really a sort of an allowed operation. I should also say that from an efficiency point of view, doing things that way is a terrible idea. Because say I have 50 qubits, right? So to send you a quantum state of 50 qubits, I just have to send you 50 qubits, which is within the realm of possibility. But if I wanted to instead send you the wave functional via a classical channel, right, then I have to send you 2 to the 50 bits, classical bits, to send you the same state, and that's totally impractical. So you lose the whole. The whole point of quantum information is that you can get around that 2 to the 50 by actually using qubits instead of bits. Okay. So we can't clone, and so we can't do the repetition code. But it turns out that there's something else that we can do instead. So the basic idea of quantum error correction. So this is that. So what quantum error correction says is instead of doing this, the idea is that we store the message using entanglement. So here there were 8 bits, so maybe we turn it into 8 qubits or something. And then the idea is we store the message in the different ways in which these guys are entangled with each other. And then because entanglement is a non-local property of the system, it's something where it can be robust against storing up 1 qubit here or 1 qubit there. So that's the kind of intuitive picture.
So the message is stored in the entanglement between the qubits.
Yeah, it's right. It's stored in the entanglement between the qubits. So that's the basic idea. Now, of course, obviously, we should talk about some example, right, so that we can all see what that really means. So that's what I'll do now. And actually, we'll see that this example, at least to me, it's surprising how much mileage we're going to get out of this example. It's the simplest example of quantum error correction. But by the time we're done with this lecture series, we're going to see that it has bulk effective field theory, it has commutativity in the radial direction, it has the Ritake-Yanagi formula, it has black holes. Don't laugh at it. It's a serious example. You might say it's the simplest holographic theory. So the example is what's called the 3-qubit code. So the idea is, well, we've got some state, which is a state of a qubit. So we sum from 0 to 2, Ci, I. So a qubit is a 3-state qubit, 0, send you is going to be, I have some, some spin 1 particle is in some state, and I want to arrange at the end of the day for you to have a spin 1 particle in your lab in the same state. And we're going to work out some protocol for us to accomplish that, over a noisy channel is the terminology people would use. So the idea is that we take our 1 Qtrid state and we encode it into the 27-dimensional Hilbert space of 3 Qtrids. So I'll introduce a state psi tilde. Again, a superposition, same coefficients, but now over a set of states I tilde, which span a 3-dimensional subspace of the 27-dimensional Hilbert space of 3 Qtrids. And let's say what it is. So there will be a logical 0 state. So yeah, let me introduce. Yeah, okay. Let me say this first. There'll be a 0, an encoded 0 state, which is in the so-called GHZ state. There'll be an encoded 1. 0, 1, 2, plus 1, 2, 0, plus 2, 0, 1. And then, of course, there'll be an encoded 2 state, which is 0, 2, 1, plus 1, 0, 2. And can we guess what the last one will be? 2, 1, 0. Okay, and so then the language we use to describe this situation is we say that there are 3 physical Qtrids and 1 logical Qtrid. So if this were like a quantum computer, then the 3 physical Qtrids would be like superconducting crosses or Josephson junctions or something like that. Right, they'd be the actual Qtrids. And then this 1 logical Qtrid would be the one that you use to do Shor's algorithm or something, right? It would be the one that you're actually manipulating.
I couldn't figure out the pattern, please.
What?
What is the pattern that you used?
Oh, okay. Well, so this one is easy to remember. So this one and then this one, I guess you just have to see. And then here, I just took this one and I flipped the second 2 in each.
Last two.
Sorry, the last, the second 2. Yeah.
First we remember this.
Yeah. So the important thing though is that all the states appearing here are orthogonal to each other. So once I use 0, 0, I don't get to use it again. So
But is there a way to think of, so the first one is this
GHZ state, yeah.
Are the other 2 sort of well pairs in some way?
Well, the other ones are also GHZ states. They just differ by basis transformation. Yeah, they're GHZ.
So they're all using 3 GHZ states.
Yeah, that's right. And so right. So let me emphasize. So these states are symmetric between the 3 Qtrids. So that's convenient because that means we just have to discuss how many Qtrids are involved in whatever we're doing without
Before that. The first line was you have a product of 3 Hilbert spaces.
Sorry, here or here?
No.
Yes.
Here it's a direct. I have 1 Hilbert space which is 3-dimensional. It's a direct sum of 3 1-dimensional Hilbert spaces, if you want to say that. But
So if you open this out, what are the states? I equal to 0.
so here the states are I equals 0, 1, and 2.
That's it.
That's a basis. Yeah. So because that's the logical system. It's 1 Q. Right. The message has 1 Qtrid. So then it's we describe it with a 3-dimensional Hilbert space. But then the idea is, well, okay, but so I could just say I have a spin 1 particle and it's in this state, and I'm just going to send you that particle. That's sort of the trivial channel, so to speak. But then say that if there's this 10% chance that it gets screwed up, then there's just a 10% chance that it gets screwed up, and maybe that's too high. So the idea is that instead, by picking a subspace out of the larger Hilbert space, we might be able to decrease the probability of error.
I'm not saying it's symmetry.
It's
0, 1, and 1.
It's permutation symmetry between the 3 Qtrids, right?
suppose I take number 1 and I
Yeah.
exchange the first and the second. So I get a 102 from the first one. I don't see 102.
Oh yes, yeah.
Second of the last, the second of the third.
No, but then that's interchanging one bar with 2 bars.
No, you're not
The first one, if you exchange anything,
First is
it will
fine.
be same.
Look at the second one.
Second
one, exchange the first 2 qubits.
You
0, 1, 2 will give you a 102. I don't see 102.
It's not full S3, just that.
yeah, it's cyclic.
It's cyclic
Yeah,
symmetry.
cyclic symmetry. Yeah, recyclic symmetry. Yeah.
I mean, these are like the untwisted sectors and maximally twisted sectors of S3.
Right. Yeah. The highbrow way of saying it.
The only thing that you want to require here is you have orthogonality between 0 tilde, 1 tilde, and 2 tilde, and each of the rows and columns are also orthogonalities.
Yeah. But I mean, so far it's not clear what I'm going to use this for. So unless you're smart or you already know the answer, it should be obvious why I picked these particular states. I mean, there's a whole formalism for coming up with these kind of things, but we're just going to do experimental physics here. So we'll see that if we do this, then it's good. Let me make another comment, which is that all of these states are very entangled, right? So none of these are close to being a product state between, any pair, 2 and 1 of the qubits.
And probably maximum. If I trace over one of them, then at least what I get is a maximum.
If you trace over 2,
Over two.
if you trace over 1, no. And actually, we'll see that in a second. Okay, so now I'm going to make a claim. And I won't do the proof just because it's tedious, but it's a homework problem for you to check. So the claim is there exists a unitary acting just on the first 2 tensor factors of the Hilbert space. So by that, I'm always a little bit careless about writing tensor factors with the identity. So when I read U12, I mean an operator that acts non-trivially on the first 2 qubits and acts as the identity is a tensor product with the identity on the third. So there exists U12 such that if we act with let me put it this way, that I tilde, so these 3 states, so I goes from 0, 1, and 2, is just equal to U12 times I on the first qubit times a state I'll call chi on the second 2, where chi is some maximally mixed state. So it's not obvious that such a unitary exists, but I claim one does.
I'm not sure I understood that, sorry.
Yeah.
So chi 2, 3, of course, you've given us explicitly, but I or 1, what is that?
So I is a number here. I is 0, 1, or 2.
0, 1, or
So
2.
the idea is you can substitute in whenever you want. So
Okay.
if you put 1 here, you get 1 there.
Okay. And the unit, there's one given unitary transformation.
Yeah, independent of I. That's the
Put in,
important
put
thing.
in
It's
whichever I.
independent of I. You have a fixed U12, and this is true.
Okay, got it.
So you can construct the U12 by looking at this expression for chi and then thinking about what you would need to do to the basis states. And I'm looking at this formula. So in 5 minutes, you'll be able to construct what the U12 is.
So this means that after doing this unitary transformation, it's like all the information was in the first factor.
That's right, yeah. So it means up to a unitary on the first 2 qubits, you can think of all the information as being just in the first qubit.
That's the sense in which you made it redundant by
Yeah.
going to this tilde variable.
That's right. So in particular, what this means is, say I prepare this state psi tilde in my lab or whatever, and then I put the 3 qubits in separate boxes and I send them airmail to TIFR. But somewhere in between, the 3rd qubit falls into the ocean, or some bureaucrat loses it, or who knows what.
Doesn't get a visa.
Doesn't get a visa. No, that's going the other way. Right. So say that we so I send you psi tilde and I send you the 3 separate boxes, but then the third Q-trait is false. But you receive the first 2. So then you say, oh well, great. So I'll go downstairs to my experimental colleague who has a quantum computer, and I'll get her to act with U12 dagger on the 2 Q-traits that I got. Right. And now, hey, look. There's psi on the first Q-trait. And then you're missing half of chi, but who cares? So you have the other half of chi. It's some excellent state. You throw it in the garbage because you got the state here. And then the fun thing is that by the symmetry, this means that there's also U13 and U23. So whichever 2 of the Q-traits you get, there will be some unitary you can use to decode the message.
And how would you know which one was the gobbled?
Good, yeah, so that's a good question. So here I'm assuming that you know. For the same reason that in AdS CFT, I'm assuming you know which boundary region you have access to. So technically that means I'm assuming what are called erasure errors instead of what are called depolarizing errors. The difference being for erasure errors, you know which got erased. So one way you can think about that is when I send you the state, I put labels on the boxes, 1, 2, and 3, and so you look at the labels to see which, whether you got 1 and 2, or 2 and 3, or 1 and 3.
But I guess what's being asked is you got all 3, but 1 got corrupted somehow.
So but erasure, right, so that's what I said meant by erasure means either you receive it or you don't, and you know if you don't, and if you know you received it, then it wasn't affected. So, indeed, so there are more general models. So for a quantum computer, that's not a good model of how the errors will work. But it turns out usually that if you can protect against erasures, then usually you can protect against other errors too. It requires something a bit more sophisticated than what we discussed here. And at least so far for AdS CFT, the problem we're interested in is an erasure problem because we know which subregion of the boundary we have. And there's not really an environment screwing things up. We're just, by hand, tying a hand behind our back and then asking what we can still do. So the erasure is the best model.
I mean that in AdS CFT you're saying, okay, you have access to some region of the boundary, according to some rule or whatever.
Yeah, that's right. Yeah, and we want to know what information we can access. We'll make that parallel more precise in a sec. But
So this 1, 2, 3 will be the 3 regions in the
of course, yeah. So this should be reminiscent of what we were just discussing with the 3 things. Yeah. And indeed, now let's. So let me now make that a little more explicit. So here it doesn't quite seem the same because there we were talking about the operator, and here we're talking about states. So let me first translate this into a statement about operators. So say that we have some operator on the Hilbert space of a single Q-trait. Which acts with these matrix elements. And so these are just arbitrary matrix elements, can be any operator on a single Q-trait Hilbert space. So in the language we're using here, I'm going to call that a logical operator, because it's the kind of operator that you'd want to apply with your quantum computer, although usually those are taken to be unitary, but here I'm not going to restrict to that. So then we can always find some operator on the Hilbert space of 3 Q-traits, which acts with the same matrix elements on the encoded subspace. Right? I mean, just by definition, there's a subspace, and we don't care what it does on the rest. And I should also, I'll write this line once, but then it'll be implicit from now on. I'll also demand that if we act with the dagger, it's also compatible. So roughly speaking, the dagger in the larger Hilbert space is compatible with the dagger on the code subspace. So from now on, I'll say same for the dagger every time, so we don't have to keep writing this. So this is a logical representation of this operator, but this tilde right, we haven't fully specified it because we just said how it acted on the 3-dimensional subspace. right, and it's important, right? Both lines are important because this makes sure that it never takes you out of the subspace. Right? Okay,
So
so
why doesn't the second line imply that?
these two? No, this doesn't imply that, right? Because the matrix could have, right? You could imagine like here's the code subspace, right? So here's the orthogonal complement of the code subspace. Then you could imagine this line tells you that I never worked out. I think this is 0, but this might not be. So then I want this to be 0 too, and so that's why I put the right. And then the logical operator is here, and then whatever goes here we don't care. Okay.
The code subspace is this three-dimensional.
Oh yeah, sorry. Yeah, I meant to introduce that. Yeah. So this subspace is called the code subspace. So the code subspace is the set of states that we're using to represent the logical qubit or qubit, and then errors can take us out of the code subspace possibly. Yeah. Okay. So in general, though, if we just pick this subspace arbitrarily, then we'll always be able to find some O tilde that does this, but in general, it might have to act non-trivially on all three of the qubits. There might not be a O tilde doing this, which also acts trivially, with the identity factor on one of the qubits. But in this particular case, we're in luck. Right, because we can use U12. So what we can do is we can first act with U12 dagger to decode the message, and then we can act with O just on the first qubit, and then we can re-encode. And so if we do that, then indeed this implies that that O12 acting on psi tilde is equal to O tilde acting on psi tilde for all psi tilde in the coded subspace, which is the span of these. And this will be the first place where I say and the same for the dagger. All right. And so you see, but then right, and then now obviously there's also going to exist the O13 and the O23. So indeed we've now seen that any logical operator on the code subspace can be represented on any two of the boundary qubits. Let's say the physical qubits. I'll use the polygraph which way.
So if you want to recover a coded operator, you do the reverse of the operation that you told us about,
Yeah.
and then project onto the Hilbert space.
Well, I'm not sure quite what you mean. So I mean, this is if I measure this, if I just measure this operator, and I know that the system is in a state which is in the code subspace, then the statistics will be exactly the same as if I had measured, this operator in the unencoded system, or this one.
Right, suppose somebody sent you the message,
Oh yeah,
and you wanted to now deal with a particular operator.
yeah,
So you take that message,
yeah,
similarity transform with U
yeah,
to get to the
yeah,
operator acting just on Hilbert space 1,
yeah.
and then process it.
Yeah, I mean, you can say it either way. You can say I decode the message and then I just measured this operator O1, or you can say I take the encoded message and I measure this operator O12, and the statistics will be the same either way.
Yeah, but it's for error correction, you
Yeah.
don't want to do that, right? You want to.
No, actually, usually not. So usually you never want to decode because while you're decoded, then an error could come and hit that first qubit. So it's better to do everything encoded and measure these complicated operators. Yeah.
In effect,
From our point of view, it's the same. Yeah. Experimentalists take care about devices. Yeah. Okay. So good. So you see that we've got a situation where we can reproduce this funny business about the operator being able to represent it on any two of the regions. Now, moreover, so something else. Oh, actually, let me write it here. And then there's something else interesting also that happens. So that was kind of like our third puzzle, but we can also make contact with the first two puzzles related to radial commutativity. So So say we look at the commutator of any logical operator with an operator that acts, say, only on the third qubit. And then we compute its matrix element between two states in the code subspace.
Let me just understand this. X3 is an operator acting on the third qubit.
Yeah, X3 is an operator on
O tilde is a general operator acting in the fourth subspace.
That's right.
Okay.
Yeah.
All right. And phi tilde and psi tilde are two states.
Two states in the code subspace. Yeah.
Thank you.
So then you see O tilde is always acting to the left or to the right on something in the code subspace.
Right.
So then by this equation together with its dagger, we learn that we can just replace this by O12 in this calculation, but then it's 0. Because these are now acting on different physical qubits. And had we, instead of 3, had we put 1 here, then I would have put O23 here. And so you see that within the code subspace, this logical operator is going to commute with all single qubit operators. So that was kind of like in holography, having an operator in the center which acts non-trivially but commutes with all of the local operators. And the way we avoided a contradiction is because we asked this only within the code subspace, right? Which is this point that Subrat had been emphasizing.
So does it mean that it's like this kind of an operator is one on, I mean, yeah, how does it avoid Schuh's lemma? I mean,
well, it avoids Schuh's lemma because this commutator is not 0 as an operator equation.
yeah, so I'm
It's
saying
equal
that,
to an operator which is
Does it-
0 on the code subspace and something else on the orthogonal complement of the code subspace, and that's enough. The key, so quantum error correction is all about the interplay between the tensor factorization of the big Hilbert space and the choice of the subspace. And the choice of the subspace doesn't play nicely with the tensor factorization, right? All the states are very entangled. And so the mileage comes out of that. So now let me just state very clearly how the analogy with holography is working here. The bound are 3 qubits. Are the boundary theory. So the CFT is our 3 physical qubits. So this is a lattice CFT, if those words make any sense. The lattice QFT.
Sorry, say you only 3 points.
3, yeah. So it's a lattice with 3 points.
Okay.
So our boundary theory is very simple. It's a lattice theory with 3 sites. And the tensor product of the degrees of freedom in each gives you the full Hilbert space of the boundary conforming field theory. Then, so the bulk effective field theory corresponds to the one logical qubit. So our bulk theory is even simpler than our boundary theory. It has only one lattice site. So we've got our causal wedges like this. So our one bulk point is sitting inside of the causal wedge of any 2 of the boundary qubits, but not inside the causal wedge of any one of the boundary qubits. Okay.
So sorry, so just to understand, you're making a model here where, let's say the boundary has 3 points and
Yeah.
I guess and a qubit at each point.
Yeah, qubit at each point.
And then the bulk has a qubit in the bulk. So
Yeah, in the center.
in the center. Okay, good.
And now we see we've achieved radial commutativity. So we've achieved that this guy in the center commutes with all of these guys as required by causality in the bulk. We've achieved that this guy has an AdS Rindler reconstruction on any of this.
Sorry, a bit slow. And then the Hilbert space, or are we talking in terms of operators, I guess?
Yeah, operators. Yeah.
Operators, okay.
Operators.
So the operator in the center is
Yeah.
the analog of the O tilde operator?
That's correct. So O tilde is like a bulk field sitting at this point.
And you're measuring the commutator only in the code subspace.
That's right.
That's the key.
And that's the key. Yeah.
That commutator in the code subspace commutes is zero for
Yeah.
anything with anything
Right.
only one or only two or only.
That's right. So the point is that as far as the measurement theory of somebody who finds themselves living in a state in the code subspace, we can think of these guys as self-commuting. So and that's how we avoid the time slice axiom. I mean, of course, here the time slice axiom is a theorem, right? So on the full Hilbert space, if you have an operator that commutes with all the single qubits, then it's a trivial operator.
This code subspace is not like an irreducible, representation of something in any sense, because then there would have been a mini Schutz lemma in that
Yeah,
part,
that's right.
which would have said that O tilde can only be identity in that part.
Right. But you can't, just within the code subspace, there's no sense of this tensor factorization. Right?
Yeah.
So that.
Because it's so infinite.
Yeah. Because it doesn't factorize.
Yeah, you're not saying that O tilde commutes with all other operators that act on the code subspace. You're saying that it commutes with operators that act only on one,
Yes.
or only on two, or only on three.
Right. In fact,
So there's no
there are-
representation theory.
Right. In fact, I mean, there are operators that doesn't commute within the code unless you pick code.
Of course,
to be
yeah.
trivial.
Yeah.
Right. Because the code subspace is more than one dimension.
Let me try and understand that. You're saying if you took operators which are acting on the first and second qubit,
Yeah.
then O tilde won't come in.
Yeah, that's right. So for example, O tilde, I can pick X and P or something, right? I mean, here it would be X and P. So
Spin Z.
spin X and spin Z or something, or the qubit versions of those, like Gell-Mann matrices.
I mean, then O tilde wouldn't commute with that operator even that is the expectation
That's
value
right.
within the code subspace.
Would not commute, yeah. And that's essential because we're trying to do bulk quantum mechanics here, right? So in bulk quantum field theory, there is a non-abelian operator algebra. So here O can really be an arbitrary operator in the code subspace, including, right, this preserves the algebra, right? So like this equation, if this equation is true for every O, then it preserves the algebra, O1 times O2 or something, right? It's mapped to O1 times O2, right? So you're really simulating the whole algebra of operators in all of the measurement theory.
And it's the analog of the fact that the bulk operator could be reconstructed from the boundary using 1 and 2, and therefore can't commute with operators, one and two operators.
Yeah, that's right. Because you could imagine, right, you have a field here, but so you'd say you have phi and phi dot here, right? So those are non-commuting bulk operators at this point, and so I can represent them both here. So then I must be able to get that algebra.
I mean, you're saying, sorry, just trying to understand, you're saying there are operators in 1 and 2 which don't commute with each other.
Yeah.
And
But I mean, to be clear though, we're not interested in arbitrary operators on 1 and 2, right? I mean, these are specific operators in 1 and 2 that act within the code subspace.
yeah.
But there are operators that act within the code subspace and have their support only on 1 and 2, which don't commute with each other.
Yeah.
And we need that.
Which have within the code subspace.
Yeah.
All these operators can be faithfully represented in terms of O tildes. An operator acting on any one of the qubits can be.
No, so, well,
Acting on any two can be. Is that the point? That is,
No.
the U could act on any two, so go ahead, sorry.
yeah, well, let's first hold the 1 and 2 fixed, okay?
Yeah.
The point is that just acting on 1 and 2, I can make operators an arbitrary operator in the code subspace can be represented like this, right?
I mean, any operator acting on one, O1, that is, can always be lifted to an O tilde.
Yeah, that's right.
Yeah,
Right.
that I understand.
Yeah, but in particular, it can be lifted to an O tilde, which only acts on the first 2.
On the first two. That
I
also-
think there's an issue
I
here.
got it.
I think you're conflating the logical Q-trip with the first physical Q-trip.
Oh, that
Those are
might be-
different things.
That might be.
Those are different
Okay,
things.
Let me understand.
The logical
logical Q trait is the code subspace.
That's right, yeah.
Yeah, no, that I
So
that I
this
saw.
U sort of decodes things, but you never, the decoded state doesn't have a physical interpretation. I just use the U to construct this operator.
Yeah, that's fine, that's fine. It's when we started talking about operators which didn't act on the first or the second, but simultaneously on both.
Yeah.
I got a little confused because then this map,
But this is such an operator, right?
this is such an operator, but I meant if instead of O1 itself,
Yeah.
I mean, I had something which acted on both the first and second, I could still do the U dagger.
Oh, you could, but that wouldn't necessarily give you anything next.
Yeah, because and that's what sort of started getting me confused.
But yeah, I would just not worry. Just don't think about it. That's not the thing that we want.
Since sure was
No, it's the X3 that I'm talking about. You see, suppose you replace X3 by X23 or X13.
Oh yeah.
That will not compute.
That will not compute in general. Yeah. So yeah, that's certainly true. Because in particular, I can think this to be another logical
That
operator.
is certainly not.
Yeah.
Yeah, and that is the analog of the point that your bulk operator cannot be constructed in a way that will commute with all operators in two regions of the boundary.
Yeah, that's right. Only with.
That's what I meant to say. Sorry.
Okay, all right, I was getting confused.
But
Okay,
we're okay with that because given 2, then the causal wedge includes this point,
Yeah.
so we don't need it to commute. All right.
So the tilde, I think, is best to just think of the code subspace and then whatever you get from, not the other way.
Yeah, you should just think in the tilde variables. The decoding was what you would do if we were sending stuff in the mail and so on, but that's not actually what we're doing. We're doing this. You know, we're measuring the physical fields are the encoded operators.
Can I generalize this just from the point of view of the bulk reconstruction?
Yeah.
Can I generalize this to a situation where the bulk point cannot be reconstructed by any 3 regions, but it can be, cannot be reconstructed by any 2 regions, but it can be by 3. That is, was there something, there's something nice about, was there something nice about the 3 region example here, or does the story get?
Well, we're going to generalize.
Oh,
so maybe wait a little bit and see. Right. So far, it's just some example. I mean, of course, I wouldn't present this to you if the lesson was in general. So.
But you need at least 3, right?
What?
But you need at least 3 agents. You can't just do.
Well, to do the paradox I was doing, you need 3, yeah, because it was phrased specifically in terms of 3.
The whole error correction story won't work with 2. I mean, if it.
Yeah, because of cloning.
So, or more precisely, if you had some code which protected against the erasure of 1 qubit out of 2,
Yeah.
then it's just setting into.
Yeah. Oh, yeah. So sorry. But okay.
Yeah.
Let me say that. Let me say what you're saying differently. So say you imagined that you had a code where it had 2 factors, and then you could recover the message from either factor. Okay. That clearly can't be allowed because then that would be a cloning machine. Because it would mean that you feed in 1 logical state, and then you can get out 2 from the 2 sides. So it's a general principle that if I can reconstruct from some subset of things, then I can't from the complement. And that's consistent with what AdS Rinder was telling us too.
Yeah. No, what I was roughly trying to ask was that the moral here is that you could reconstruct the bulk point by taking the 2 regions on the boundary, but not 1.
Yeah.
Because the state, the way holography works is that the state in the 3 regions on the boundary are highly entangled.
Yeah.
So just as your GFC, whatever states are highly entangled, right? And then I was wondering whether in fact this generalizes so that if you took some appropriate point in the bulk and some smaller regions on the boundary, any 2 regions couldn't get to the bulk, but 3 regions could get to the bulk. So and so on and so forth. So there's a very, very intricate entanglement in the boundary.
Yeah, that's right. That's right.
That's
Yeah,
what
so
I'm
you're gonna see
All
that.
right, so go ahead. It's not to work like that, but
Just break 1, 2, and 3 up into 2.
yeah.
So we're gonna the example we'll discuss at the end will have n qubits and k qubits. All right, so let me make a few comments now about this. So comment number one is that the entanglement in pi is essential for this to work. Okay, so let's understand again why that is. So we have this formula that psi tilde is v12 acting on psi 1 times chi 2, 3. So now say that chi was a product state. Say that this were, chi 2 times chi 3 or something. But it would have to be the same, phi 3 or something. So then, what this would be telling you is that the information is really just contained in 1 and 2, right? Because we can just pull, this u doesn't see this factor, so we can just pull this factor out and it's irrelevant. Whereas in fact we know that this 3 is very relevant because, if we're given just 1, then we don't have the message, but now if we're given 3, we have it again. Okay? So it's very important that chi was entangled. That's what gives you this robustness of being able to have u12 and u13 and u23. And maybe just to give you a teaser, we'll eventually see that the entanglement in this chi is what's responsible for the area term that we're talking about. So then it's important that there's a lot of entanglements in chi. Okay. Okay. Another comment is that so there's a whole general theory of this, and we're not really going to be able to get into the whole general theory because just time is finite and there's too much stuff to talk about. But this general picture of the state is more or less correct in general. So if we have in general, if we have a boundary Hilbert space that factorizes into A and A bar, so you can think of that as being like a region and its complement. Then there will be some unitary acting on the region which we have access to. And then there will be a state psi, which is on some subfactor of A, which has the same dimensionality as the code subspace. So here this is like the first Q trait out of the first two. And then there will be some state chi on the rest of the region we have access to, and then on the thing that was erased. So not only is that how it works here, this is how it always works. In any error.
Even in some NQ.
Yeah, in any error correcting code.
Is there a sense in which the number of spurious stuff that you have to add grows with the amount of data?
Yeah, that's what we're going to discuss now.
Grows with the amount of
Data you want to.
I'm going to write inequality here.
Yeah.
So let's say say that there are n total qubits or Q traits or whatever, but I'll just say qubits, and k logical qubits, right? And moreover, say that.
by that you mean the dimension of the code.
Yeah, so the code subspace is 2 to the k dimensional, right? But the interplay between these qubits and these ones involves some complicated changing bases. And then finally, let's say that we want to protect against L erased qubits. Okay, so let's look at this equation. So this is k qubits. Right, because the dimensionality of the sort of unencoded message is just the dimensionality of the code subspace.
Sorry, which was L again there? Or what did you say?
I haven't mentioned L yet.
Okay.
L is the number of erased qubits.
Okay. So that's K, you're saying.
K is this is the message, right? So K is the number of logical qubits. So this Hilbert space, right? So here was 1.
Mm-hmm.
Right. So for us so far, this was 3, and this was 1, and this was 1. And then, so now I'm gonna make a technical assumption based on the observation we just made about this chi having to be entangled, which is I'm going to assume that the density matrix on this factor, let's say, has full rank. On A bar.
On A bar.
Yeah, I'm assuming it has 4 yeah, essentially that's saying that it's not, that you don't just have some pure factor here sitting in a bar that you can pull out.
Actually, what was A bar? Is that?
A bar is the region that's erased. So A is A is
Yeah.
right. So say it's 1 and 2 is
So
like
it's
A.
3 in the-
3
yeah,
is
yeah,
3 is
three.
A bar. Yeah, it's the complement of the region you have access to. So now this guy we can write its dimensionality in 2 different ways. So obviously one way of saying is that there are n minus k of these, right? Because n is the total number of qubits. But then we can also say that this is equal to L, which is the number of things in a bar, plus delta, where I just made up delta. It's a symbol for the dimensionality of A2. Right? So these were both 1 before. But now, if we assume that A bar has full rank, that means that the density matrix, the reduced density matrix on A bar has L non-zero eigenvalues. Or should maybe, I think I should say 2 to the L non-zero eigenvalues. Yeah, so think of it as being the identity, right? So for simplicity's sake, chi is maximally mixed. So then there are 2 to the L non-zero eigenvalues of rho A bar. And that means that A2 must also have, since this is a pure state, A2 must also have 2 to the L non-zero eigenvalues, which means in particular that L needs to be greater than or equal to, that delta needs to be greater than or equal to L. So if delta is too small, you can't purify a full rank density matrix on A bar. Yeah, so this is a general fact about entanglement. So if you have a pure quantum state, then the number of so all of the non-zero, so say between A and A bar. Let me say A and B so we don't get confused about the symbols here. General fact about quantum mechanics. So you have A and B who are entangled in a pure state. So you have some pure state psi A, B. Then the non-zero eigenvalues of rho A have to equal the non-zero eigenvalues of rho B. Okay? That's a theorem in quantum mechanics, and it's the reason why the entanglement entropies are the same for A and B. So in particular, not only does the number of non-zero eigenvalues have to be equal, but the non-zero eigenvalues themselves have to be equal. But I'm not using the stronger statement here. For me, it's enough just to say that the number of non-zero eigenvalues is equal. So since I assume that A bar, that chi A bar has full rank, that means that it has 2 to the L non-zero eigenvalues. So that means that chi A2 must also have 2 to the L non-zero eigenvalues. And so clearly for that to be possible, then the dimensionality of A2 has to be bigger than or equal to the dimensionality of A bar. So that tells us that this delta, which is just the dimensionality of this A2, has to be greater than or equal to L.
So for the thermophile double, it's saturated. Delta is equal to L, right? You have one. If you have a thermal density matrix which you want to purify.
Oh yeah, that's right. They're equal. Yes, that's right.
A2 is just.
Yeah, then they're equal. And so that'll be the case for the same quality of saturated. So now let me. I'm running out of space, but let me write it here. So, Subrat, can you guys see the bottom of the board here?
Yeah, I mean, as well as they can see the top.
That's terrible.
All right, well, I'm sorry.
No,
So let me say, so if we combine, so we know that L plus delta is equal to n minus k, and we know that delta has to be greater than or equal to L. So I can eliminate delta, and we get an inequality which says that n has to be greater than or equal to k plus 2L. So that was the result I was trying to get with this comment. And this is what Shiraz was asking. So what this says is, if you want to send a bigger message, more logical qubits, and you want to protect against more erasures, then you're going to need more physical qubits.
Your last example was n equals 3, k is equal to 1, L equals 1.
Right, so that was what I was going to say. So our last example was 3 equals 1 plus 2. Yeah. So show, although I won't, that so this shows that this is necessary, right? But in fact, typically it's also sufficient. So you can show by, if you choose a random subspace, so you start with n total qubits, you choose a random 2 to the k dimensional subspace, then you can show using sort of Pagean technology that as you get on the right side of this inequality, you sort of win exponentially. So you get closer and closer to being able to reconstruct, to correct for the error of erasing any L of these bits.
So in general, what's the reason that chi A bar needs to have full rank on A bar?
Yeah. So that I kind of put in as an assumption, but I motivated it by pointing out that the entanglement in chi was important for the redundancy of the code. So you see, the thing is, of course, if we keep the A and A bar fixed, right? So we just talk about splitting into 1, 2, and 3. Then chi could even be a pure state. It doesn't matter. Right? But the thing is, we kind of know that in good codes, you want to be able to correct for different erasures simultaneously. And we saw here that required chi to be entangled. So,
I have a question.
yeah.
There's something that's bothering me a little bit about this. If you just had a three-field theory, for example,
Yeah.
you could still do a lot of this, right? So you could divide it into different regions, and you could get a lot of the same structure.
So you mean a free field theory in the boundary or the bulk?
A three-field theory in the boundary.
Yeah, that's true. Yeah, no, but I haven't reconstructed, Lorentz invariant gravity with locality below the AdS scale either, have I?
Right, I understand, but the only question I had is there's something special to holography, which is that in holography, if you look at the light operators in the boundary,
Yeah.
you're not able to annihilate the vacuum by acting with them unless you smear them on the time scale of at least pi.
Yeah.
Somehow it's entangled with respect to those operators, and that's somehow not visible in this regional entanglement, which also exists in the three-field theory.
Oh, so let me see. So
But yeah.
let me understand. Sorry. So your worry is that, okay. So let me see if this is the same thing as you're saying. So in particular, we have a O, 1, 2, and let me think how to say this. Well, I guess in the Qtret example, it's not quite good enough. But so say we're doing AdS Rindler, and I have an operator here, which say I can reconstruct either here or here. Right. So there's a reconstruction like that, or a reconstruction like that. Then, if I take the difference of these two operators, I get an operator whose support is in a finite region, but which apparently needs to annihilate the code subspace. And that seems in tension with boundary Rischlider. Is that what you're saying?
No, actually, my question is just, there should be something that, I'm worried that the structure we're getting is too general, because what is it in the structure that tells us that a three-field theory of the boundary doesn't have a bulk locality?
Oh, no, but it has bulk locality at the AdS radius, right? So I completely agree with the sign of your comment, which is that, quantum error correction is not like, I'm not saying quantum error correction equals holography with an Einstein holography, right? The claim is that Einstein holography is like a subset of quantum error correction. And quantum error correction has features in it which are able to solve the kind of problems we were talking about, but I don't want to say that it solves automatically all the problems of holography. Clearly, even just if we look at CFTs, right? Well, as we discussed in the first lecture, right, it's a small subset of CFTs that have locality at the AdS radius. The interesting thing here is that locality sort of at the AdS radius at least can be solved quite generally. And even below the AdS radius, from the bulk side, we derive these things, right? So apparently they're going to be true.
I understand, but there is something about a three-field theory which will tell you immediately that it doesn't have a good local equivalent. That is the fact that if you take whatever you call a simple operator, which is just a three-field operator,
Yeah.
and you introduce them on a single time slice, you
Yeah.
can already generate an annihilation operator, and you will be able to kill the vacuum.
Yeah.
And that tells you if you take a band of any finite thickness in the boundary,
Yeah.
you're already seeing
somehow the bulk reconstruction is kind of simpler. I don't know. I mean, somehow you don't, there's some sort of genericity, which is not true in the free field case because the degrees of freedom just stay at the boundary, right? So there sort of aren't really any bulk operators to reconstruct in the center in the first place.
Yeah, okay. I mean, I don't have much more to say, but just the fact that the vacuum is separating with respect to the simple operators in the theory should somehow be important, I feel, which doesn't seem to be.
Well, yeah. So I mean, let me be the first to acknowledge that holography has many special. I mean, so far this is a toy model, right? I mean, I don't want to say this. I mean, obviously this is not holography, including all of the properties that we think, large N Yang-Mills theory has at large lambda. Right? But it has the particular properties that we found puzzling. That's the right. And like with any toy model, we have to pick which features we get and which features we don't get. If we have all the features, it's not a toy model, right? Yeah. Okay. Let's see. Where was it? Ah, yeah. So we had this. So we had this in inequality, which we're going to use in a minute to test this against AdS CFT. All right.
Say what this means in terms of volume. What this constant means.
I'm going to tell you.
Okay.
Yeah, I haven't told you yet, but we're gonna see that in a minute. But the point here is that we derive this inequality from the CFT side. Okay, so then if we see it reproducing bulk physics, that's a test of this idea. All right.
I mean, roughly speaking, the idea is that since you're encoding information in entanglement, if you want to erase L qubits, and you have 2L of them in addition to the ones to the actual message, then you'll still be able to recover the message. Because you lose L, but the L remaining will, because of entanglement.
That's right.
Oh, I just need to repeat.
Okay. So that's all I was going to say about the example. Here are the two comments. So now let's start thinking about what kind of code AdS CFT will be.
This is going to tell you roughly that if given a region on the boundary, how much of the bulk can it?
Yeah, that's right. Which is the thing we know how to also study in the bulk, so we can compare.
So K is how much of the bulk it can encode. And
Yeah. So we'll see. Yeah.
N minus L is how much you can.
Right. Okay. So now let me first make so good. So now let's go back to think about the Rindler reconstruction using this new language that we've. So the first thing I want to say is that this relates the radial coordinate to the quality of protection. So let's consider some bulk operator which is sitting here near the boundary. So this operator has a representation in the CFT just living here. So that means if an error happens here, if we erase this orange region, we lose the operator. Because remember, if we can reconstruct it here, we can't reconstruct it on its complement. So this is not a very well protected operator. And from the AdS CFT point of view, or from the Rindler reconstruction point of view, it makes sense, right? Because we know in the limit this is going to become a local operator in the CFT, right? So that's like an operator that just acts on one of the physical Q-trends. And so that's clearly not going to be a very well protected operator. But as we move in, so say we consider this operator here, or maybe we do an intermediate step, consider this operator here, we see now we need a larger erasure to delete this operator. And by the time we get into the center, we need a very large erasure. We need to erase at least half of the system. Right? So to delete this one, we need an erasure that's something like that. So we learn. So this gives a so people always talk about oh, there's some relationship between scale and the radial direction or something in AdS CFT. But this is a much more precise version of that, right? Because here there's actually a thing. We ask, what is the sort of smallest boundary region where we can represent this operator? And that gives a monotonic function, which is sort of a boundary stand-in for the radial direction. So this is a very sort of concrete sense in which we can see the emergence of the radial coordinated bulk.
So something's wrong. Okay.
Yeah.
So I can look at the operator closest to the boundary, right?
Yeah.
Now I can turn it around and say it's actually protected against the erasure of like 99% of the boundary.
Yeah, but right. But you don't. But the idea is you don't get to pick the errors that happen. So the error where the erasure where you screw all that up is unlikely, right?
But there you did, when you derived that equation, you did pick a bar.
Yes. But
So
I was going to come right. So, but remember, I said this was necessary but not sufficient, and then I said that typically it was sufficient. But here this one is kind of not typical, right? It's near the boundary.
but given the necessity is broken here, right? Because there's no way A2 here is as big as
Yeah, but it's kind of related to this assumption that, right? Because I mean, of course, you can always just pick a code where you put the message in the 10th qubit, and then as long as nothing happens to the 10th qubit, then the message is fine, right? So, but if something happens to the 10th qubit, you're screwed. And so operators that are near the boundary, it's more like that, okay? So in this argument, I avoided that in two different, right? I avoided that first of all by talking about the maximum mixing of the state bar. But also still, I just said that this is, right, that kind of led to this being necessary, right? But necessary doesn't imply you can actually do it. Right? The sufficiency I had to assume typicality. And of course, in a typical code subspace, it won't be the case that the message is just sitting in the 10th qubit.
Okay, so basically okay.
I mean, somehow the center is the one that should be sort of the most typical because it's kind of, it's kind of furthest from the boundary, so it's sort of the most non-local, right? Now that still doesn't guarantee that it's actually typical, right? And so I mean, we'll see later. But I mean, this is somehow at least should give you some intuition for how it should work there. It's our typical enough, it turns out. All right. So
sorry, Dan. There's something that since we are going to move towards now thinking of holography and so on more precisely, there's something that I just wanted to ask you, which is worrying me, which is when we said in the last two lectures that from the Rindler wedge reconstruction, this is the region of the bulk which can be encoded and so on.
yeah.
We were basically thinking in terms of some simple set of single trace operators and some supergravity approximation, right?
Yeah.
But if we were to go beyond and to include all operators in some in the large gauge theory, then of course even on a single time slice we can encode for the entire state of the theory.
But that's no, but I mean we're always working on a single time slice, right? So the question is, given a single time slice, then if we have a subregion, what can we do?
Okay, now what I meant was, alright, so maybe I'm a bit confused, but just bear with me. What I meant was, at least to begin with, we said, okay, there's some causal wedge in the bulk, and this is the region we can reconstruct from the data in the boundary, right? And then what I'm saying is, if I took
From the data in a subregion of the boundary, a spatial
data in a subregion of the boundary. But if I took a particular time slice in the bulk, say t equal to 0 in the bulk, and I gave you the t equal to 0 state on the boundary, okay, that the t equal to 0 boundary region is of course spatially separated from the bulk. But if I gave everything about the CFT on
then you have everything.
Then you have everything.
Yeah, but that's consistent with what I'm saying, right? That's like saying that's like having all three of the Q-traits. I mean, these are just spatial. Everything here is happening at fixed time. We haven't discussed evolution at all.
I mean, what I was trying to ask was here, have we sort of assumed we're doing things with simple operators in some sense?
No, I don't think so.
I mean, otherwise, is this statement precise that we can only reconstruct some region of the bulk from in the some part of the boundary?
I think what you're asking is, okay, let me rephrase what you're asking. I think it's what you're asking, but let me say it in a way that's more indicative. Okay. So the AdS Rindler tells us or suggests to us that given a subregion of the boundary, we can reconstruct everything in the causal wedge using fairly simple operators in the boundary theory, right? Things involving time intervals over time of single trace operators and so on. Now, it's complicated if we move it all back to fixed time, but still it's some special set of operators. So you could ask, if we're given access to all the operators in the boundary at fixed time, including the ones that have nothing to do with the single integral, the single trace ones, could we go further than the causal wedge in the bulk? Right? Can I say it that way?
Yeah.
Yeah.
I thought one way of going further was to just ask him on the whole time, on this whole Cauchy slice in the bulk, but okay.
Yeah, but
let's just
then
say-
that's just the duality, right? I mean, that's just automatic.
And
That's just saying the states are, isomorphic or whatever. There is no way.
Right. Okay, we can say, can you go further? I was just saying, from the duality, we do expect to go further.
No, but the causal wedge, the causal wedge of the whole boundary is the entire bulk, right? So then, that's kind of a special case of this statement. Right, so if you consider taking this region to go all the way to here, right, then you just get the whole time slice.
Okay.
That was the sort of global
Okay.
reconstruction.
I see.
Yeah.
Okay, even in some region,
Yeah.
you went back to t equal to 0. All right, okay.
Yeah, I think you're just talking about the global reconstruction, which is the first thing we talked about.
Okay, sorry. Okay, go ahead. So you're saying you've actually included, so is this statement true that even if I included all the operators in the gauge theory, and I looked at some small spatial region, I may be able to construct more than what geometrically I'm allowed to do.
Yes, that's what I was.
Right?
That's what I
Okay,
was
that's a
saying.
better way to
Yeah.
rephrase my question.
Yeah.
I agree with you. So
Yeah.
how much, it's probably not precise how much better.
It is, and I'll give you a theorem that settles the question.
Okay.
And you can go further. That'll be the point of the next lecture.
All right.
For one.
Yeah, that's a better way to say
Yeah.
it, sorry.
Yeah, right.
So just to confirm, are you saying that the effective dimensionality of the good subspace depends on where you are in the boundary?
We're going to discuss that in a second. Yeah. We're going to discuss that.
Can I ask a question?
Yeah.
You mentioned that this whole idea of the radial directions being identified for some sort of RG scale in the
Yeah.
boundary theory.
Yeah.
This is different from that.
Well,
But
I
there
think
must be some connection.
this is better than that. I think
There
this
must be
is
some
the
connection.
precise version of that.
But there must be some connection here.
No, there is. It's kind of an obvious connection, right? So if you have an operator that's near the boundary,
Yes.
I can represent it with a small operator in the boundary. So that's like the UV, right? Large radius is like the UV in the field theory. If I have an operator in the center, I need to represent it using a big region at the boundary. So that's like the IR. So clearly the information of what's going on in here is in the IR of the field theory. The information about what's going on in here is in the UV. But before that was hand waving, and now it's equations. Okay. So now let me now let's try to make this more concrete and give an example where we say here's what the subspace is and so on. And then we can do things like compare this inequality. So I'm going to do a very simple kind of thing. So I'm going to take, well, my circles are not very circular, but okay, this is AdS, and I'm going to pick a region. I can just arbitrarily choose some region in the center, which is AdS scale size. So maybe 1 AdS radius across. And then, so following Kyriakos and Suvrod, I'll just take the span of states that I get by acting with up to k, from the vacuum, or then acting with sort of up to k local operators on the vacuum, but all in this region.
Oh, bulk operators.
Bulk operators, yeah. So my code subspace is the vacuum plus the span of whatever I can get by acting with bulk operators that stay within this AdS-sized region in the center.
Okay.
This is just a choice. I don't want to say that this is the only code subspace that could ever be interesting. This is a code subspace we can choose and then study its properties. So in particular, this code subspace, this operator that acts near the boundary, won't be an operator on the code subspace. That's already one reason why you might not like this code subspace, but we'd like to just pick this one to get started. And in general, in this business, there's no canonical code subspace. You pick your code subspace and then you see what its properties are. So this is a good one. Okay. So now let's first, whereas these guys that, the local operators in this region are operators in the code subspace. So, okay, let's first consider the case where k is order 1. So you're allowed to act with some order 1 number of operators in this region center. So then we can look at, actually before I do that, I first have to estimate n. Right, so since we're considering operators which are only in the central region, the smearing function that we use to reconstruct will vary smoothly over the boundary. Because remember, the smearing function involved this point and the point of the boundary. But if this point is always in this region, then its dependence on the other point in the boundary will be smooth. Just have some order 1 variation as we move around the boundary. So it means that the representation of this operator will not involve the UV of the conformal field theory.
Sorry, I missed something. I got up till the span. What
Yeah.
is it that you said after that? Sorry.
So this is the code subspace. So we think of K here as being, the number of operators we're allowed to act with. But to use this inequality, we also need to discuss the total number of physical qubits.
Okay.
Right? But in the CFT, that's infinite. Because, it's a continuum quantum field theory, it has infinite degrees of freedom, and so then this is going to be the useless inequality. So to proceed further, though, we have to realize that as far as these states are concerned, most of the UV of the CFT is irrelevant. Right? This is just all these states are orthogonal to states where the UV is not trivially excited. Because these operators in the center, right, they're smeared against local boundary operators in some smooth way. So most of the UV we can forget about. So we can easily coarse grain the CFT, say into sort of, regions whose size is sort of epsilon in solid angle, where epsilon is maybe 1/1,000 or something. And then, but then within each region, say if we're doing n equals 4, then there will be n squared degrees of freedom. Right? So then we should think of little n as scaling like n squared, as being order 1, or maybe order 1 over epsilon times n squared, where epsilon is some position cut off in the boundary theory, which is order 1 in units of the sphere size.
And that will depend on the size of the ball you've chosen.
Yeah, but I've chosen it to be 1, so then epsilon will also be order 1. And to get whatever accuracy we want, we might take epsilon to be 1 over 100 or 1 over 1,000, but it won't go n. That's the only important thing from what we're going to say here. Okay, so we can just throw out the whole UV of the theory. We have, roughly speaking, a matrix within each sort of delta theta on the boundary. Okay, now, so good. So now we know what n is, now we have to discuss k. So k is up to us. The first thing we can do is consider k of order 1. So we just say you're only allowed to act with some order 1 number of these 5s. So then let's look at this inequality here. Okay. So now you see, so this term is order n squared. This is order 1, so we can ignore it. And then what this tells us is that we need to have at least half of the boundary. So the erasure has to be less than n over 2. Right? So it's saying, we can erase, as long as we erase sort of less than half of these matrices on the boundary, we're in good shape.
What did L come with?
L was the number of erased qubits. So, yeah. Oh yeah. So good. So maybe let me draw a picture. Right. So we've split up the boundary into cells of size epsilon, each of which has n squared degrees of freedom. And then so L counts. It's the number of erased degrees of freedom. So it's the number of these cells that you don't have access to, and then times this n squared.
N is the complement of the region over which you have to smear the boundary operator in order to construct it.
Yeah, that's right. But you see, now we're in good shape, because we just remembered that, if we have a point in the center, you need more than half, and then you got it. Right? So that's what AdS Rindler said, but that's also what the CFT says.
Yeah, so the 2 was important.
So the 2 is important in that equation. Yeah.
So that you can derive in some theorem or something.
Yeah, I mean, the argument is more or less what I said here. I kind of sketched it, but yeah. Yeah, and to show that this was sufficient, there was some sort of typicality, which then we could debate whether the CFT is really typical enough. I mean, but here we're just trying to calibrate our expectations anyway. So.
But you could have taken all operators that acted on the center.
What?
You could have taken all operators that acted on the center, then K would have been pretty big, and then the region would have been pushed away from the center.
Yeah, we're about to increase K, so we just the one thing at a time. Let's first make sure we're happy with K is small.
So why was it being put in like this?
Oh, good. So if K, so K order 1, N order N squared tells us from this inequality that L needs to be less than or equal to N over 2.
Okay.
Okay? And so now then, if we say this in terms of sort of the number of these cells, right, then it's saying that the number of erased cells has to be less than or equal to the total number of cells over 2. So it says that you need to have access to at least half of the boundary. And that's the same thing that AdS Rindler told us. Now, I mean, the 2 probably, in terms of the precision that we're saying here, okay, you need a little bit more than half, and that's not anyways, but at least approximately.
But there would have been a contradiction if it was 3, right?
Yeah.
I don't know, I mean, what about epsilons and various things which were around? We had to divide it into
Yeah, it canceled out on both sides. It canceled out on both sides.
blocks to make the infinite degrees of freedom of. Everything is infinite at some level, right? N is infinite, so I'm not sure how much I'm going to trust.
Yeah, I mean, you shouldn't take it too seriously. It's more just along the lines of you see that it more or less works in the way that you want. And we'll be more precise soon, but I think already this is kind of telling you that you're on the right track. Okay, now let's also now consider cranking up K. Okay, so from the point of view of this inequality, clearly it's not going to matter until K becomes of order N squared. Otherwise, it'll just be the same thing as before. So let's do that. So now let's say K is of order N squared. Now we see that indeed, in order to reconstruct, L is going to have to be smaller. And at some point, we're just going to lose the ability to correct exactly, entirely. So from the bulk point of view, actually, that makes total sense, right? Because if you act with the order N squared operators here, then you're going to make a black hole, right? Then most of the states that you get won't be these effective field, won't be described by effective field theory and some perturbation of the geometry anymore. It'll be described by some big black hole. And so, indeed, I want to emphasize that that is how we should think about the orthogonal complement of the code subspace, right? So we said, I said in the first lecture, AdS CFT is an isomorphism between states. So, all this code subspace stuff, it might seem a little bit fishy, right? Why does the bulk only make sense in a subspace of the states? All of the states should have bulk interpretations, right? And they do. But the claim, for example, in the Qtrig thing is that, okay, well, how do we think about the other 24 states? The way we think about the other 24 states is that our point in the middle got swallowed by a big black hole. And then which of those 24 states you have is telling you the microspace of that black hole. And this point is far enough behind the horizon that it's sort of inaccessible to anybody who jumps in from the boundary.
But you had to know that there were 27 states to it.
What do you mean?
I mean,
What's that?
about the hidden degrees of freedom of a black hole. This analogy you gave.
Yeah.
To know that there were 27 states to begin with.
Well, I knew that. The whole discussion wouldn't have worked if I hadn't. I was using the 27, right? To talk about these local operators and so on.
Sorry, Daniel, I have a question.
Yeah.
I'm confused about something. I can't quite read the equation at the bottom, but does that say n is greater than equal to twice L plus k, which is in your paper as well, on the right hand?
Oh, this one? Yeah, that's what it says.
Okay, so I'm confused about the fact that this doesn't seem to care about where your code subspace was located. I mean, if you located it close to the boundary, the code subspace would still have the same dimension.
Yeah, that's right. That was the comment. So that was the discussion we had earlier, right? So this is necessary but not sufficient. So the example I gave is you can have a code subspace where you just put the message on the 10th qubit. And then the other qubits are kind of irrelevant. So erase them if you want, by all means. But if you happen to erase the 10th one, then you're out of luck. So in order for this to be sufficient and not just necessary, well, one thing which makes it sufficient is to assume that the subspace is typical, which will of course rule out this thing where you just say it's the 10th, the one where you just put the message in the 10th qubit won't be typical. And so what AdS CFT is, it kind of gives you a continuous interpolation between sort of typical and this stupid thing where you put it in the 10th, right? So
Typical is somehow close to the center and everything off center is atypical.
yeah, you got sort of more atypical. I mean, of course, there are different ways of being atypical, but in particular, you can just put the message in the 10th qubit, and that's what the ones near the boundary are like. So if you imagine like taking this region and just kind of moving it out to the boundary, that's what would happen.
Yeah, but you don't have to move it all the way out to the right next to the boundary. I mean, if you move it some distance away, then
Yeah, so there's some continuity, right? So it starts out being reason. I mean, it's clearly typicality has to be spherically symmetric, right? So as soon as you move, and honestly, even in the middle, it's not really typical. It's just sort of typical enough from this point of view, right? It's not like hard typical or something,
okay.
because it's still the low energy states of a CFT, which immediately makes it not typical.
Sorry, I think I didn't understand that. I was thinking something similar.
Yeah.
If you make the size of the ball inside, we call that R.
Yeah.
Then naively you could improve that estimate for little n.
You mean by looking at the geometry of this thing?
Just looking at the distance over which things
Yeah,
are
that's
together.
right. And you would decide you need a little bit more than half.
Yeah.
And that has to do with the fact that it's not really, indeed. So that somehow has to do with the fact that it's not really typical.
I see.
Yeah, that's right. So then you actually need a bit more than half. Yeah. And so we're gonna So we can learn from the bulk side sort of where exactly the boundaries lie, but from these sort of general arguments, right? This is related also to Sugrat's comment that this is kind of too general.
Yeah.
This one was to get everything right. I mean, but so far we're just trying to get these qualitative features, that more or less you need half, and then once you get to the point where the code is going to break, from the bulk point of view, that's when you need to play.
So this is intermediate range of K, where it's still in the code subspace, but the AdS cylinder is strongly modified, right?
When?
This is intermediate range of K,
Yeah.
like
You
say
mean
K is little n by 3, suppose.
Oh yeah, you mean like say K was order n?
Yeah, so little n by 3, suppose.
Yeah.
Then you would need
You're changing the coefficient here. You're changing the power.
let's keep it ordered n squared. If it's obviously
Yeah.
if it's like little k is greater than little n,
Yeah.
then of course you can't correct it.
I mean, this crossover region though is the region where it's kind of going to be most important. The details of what's going on in the bulk, because that has to do with when the black hole takes over from the thermal gas and so on, right? So I mean,
From the D3 bits.
Yeah, right, from the D3 bits, that's right. Yeah. So that kind of discussion will be used the most of the details of AdS. So here I'm just sort of trying to get sort of eliminate cases.
But sorry, just to come back to that comment you made about the black hole, that is, didn't fully understand that. So let's take K of order n squared, that case.
Yeah.
And there clearly then you're going to need more than half the region.
Yeah, and let's say with a large coefficient, just to make sure we're on the wrong side of whatever inequality.
It would be a K of order n squared with a large.
Times a billion or something.
Okay.
Yeah.
All right. Okay. So then clearly you're going to need L, bigger than.
Well, you just fail. I mean, at some point
You just fail.
Yeah.
And now, and what was your point that, all right, but in that case, most of the states you create by hitting with these operators phi on omega, if you have so many of these phi, are going to be black holes.
Yeah.
And then, how do you relate this to the L or the
well, that's just saying
erasure?
that's saying even if L is 0, you still don't get it, right? And that's kind of the limited case. So
you
if
still don't
if you hold n fixed and you increase k, then at some point, even if L is 0, you're still not going to satisfy this equation, right?
Yes.
So that's kind of, right, that's the limit where the thing has gone so far behind the horizon that it's just,
I see, but I mean, you can recreate all states in the, all legitimate states in the bulk from the boundary, right?
but
If
right.
you allow the,
Yeah, but you have to decide, right, what, I mean, so this is related, okay, so this is subtle, but, so think about from the information problem point of view. So from the point of view of classical bulk gravity, you have this nice slice very far behind the horizon of the black hole. So you say it's a black hole we make out of a shell, and then we wait for a long time for it to get more typical. You know, so then there's this growing volume. And so, I mean, from the bulk point of view, that geometry is real, right? There's this whole slice, and there's all this stuff that could be all the way in, and you know, and there's could be cloning and all this, right? But somehow we think that actually most of that geometry kind of isn't really there. Right? It's kind of a mirage of general relativity.
or it's complementary or something.
Yeah, well, right. But I mean, it's not even really observable. I mean, so I guess it's best to just say it sort of doesn't. I mean, yeah, you can say those words if you want. Yeah, but and obviously an interesting question, which this kind of crude analysis can't fix, tell you is in general how far behind the horizon can you go before you're required to quit. So let me make a more general comment here. So I would say that a lesson which I think is a good lesson to learn from this is this tells you why gravity is essential for holography, in the sense that you can't remember from the time slice axiom argument, it was clear that we couldn't have a quantum field theory in d dimensions be equal to a quantum field theory in d+1 dimensions, because you can just keep putting more and more stuff in the center, and sooner or later the quantum field theory is just going to have to admit that it's living in a lower number of dimensions and not in a higher number of dimensions. But here it's a gravity theory, and so again you can try. You can say, oh well, you're simulating this low energy effective field theory in a higher number of dimensions, but I'm going to keep pushing you, and sooner or later you're going to run into the wrong side of an inequality. Is this some kind of inequality like this? And you're going to have to admit that you're not really a local theory in d+1 dimensions. But then it says, no, I'm a gravity theory, and so right when you thought you were going to get me, then I'm going to do something else, and I'm going to make a black hole.
I'm just not seeing how the black hole is allowed, that connection between the fact that you can't erase anything that, I mean, what's confusing me is...
Well, so you're worried about the case where L is not 0. So, okay, so let me make...
I'm trying to add the words together. That is, if you couldn't encode at all in a way which protects against erasure,
so let me give you an example.
Why is that the black hole?
Sorry, what?
I mean, this formula taken on its face would say that the black hole corresponds to a situation where you can't protect against erasures at all, right? Because no L would...
Well, for this region, so there'll still be stuff outside the black hole, right? So
no,
we're
I meant
restricting
for
to
that
stuff
region.
in this region.
Yes.
So the idea is once you have a black hole that's sufficiently large, maybe this is 1 AdS radius, the black hole is 1,000 AdS radius, or something like that. Then these operators will correspond to things that are it'll be like the stuff that's and to be clear, let's take L be 0. So now we're asking about given the entire boundary, what can we access?
Yeah.
But even if L is 0, right, there are operators that might be, and the question of whether operators make sense or not isn't a question about the erasures, it's a question about the code subspace. Right? We're given the code subspace, we have a set of operators that make sense. So in particular, we can talk about these ones. Now to make the discussion precise, we're going to have to discuss the gravitational addressing of the operators, because once there's back reaction, we have to say where the operators are. Okay. But let's just say for now that they're attached to geodesics going to the boundary. So you can check that what happens, actually let me draw this here, is if you consider the causal wedge, right, and you can say this operator is inside the causal wedge. But, well, that was true in the vacuum, but then if I put a black hole here, right, there might be back reaction, and you can see that usually what happens is that causes the causal wedge to recede. And so now an operator which, acted within the code subspace, was a good code subspace operator when the subspace was small, might not be a good code subspace operator when you make it bigger, because, there might now be states where it takes you out or where it doesn't make sense. And so the limit of that is where even if you don't have any erasure, you just, but still, your operator, well, maybe it's better to draw it this way. I make the black hole out of a shell. There's some, we're way up here, so there's some long, nice slice, and your operator ends up being sort of way, deep inside the horizon sphere. It's an operator which is, from the point of view of people doing experiments here, it just doesn't make sense. I mean, I should say this, this was the sort of first pass, so this stuff may also help when we see more examples.
Sure.
Even if you just want to do answer analysis and say we know from the bulk that there's this Rindler reconstruction going, so there has to be some quantum error correction going on, and that this kind of argument tells us what it means to get out of the subspace. And then we can say, aha, from the bulk point of view, we know what happens there, it's black holes. And now we can think more about what that means.
And the fact, just to understand, the fact that things are inside the black hole are not a part of any code subspace is simply the fact that the HKLN map that we talked about in the first thing does not encode for operators inside the black hole.
Yeah, although, right, but there's a question, it does in some cases, so that's why I don't want to unqualifiedly endorse that statement, but certainly, let me think. So literally for the HKL, that's kind of true, because the causal wedge of the boundary never goes behind the horizon.
That's what I was thinking.
Yeah, but we're going to see later, similar to what he was saying, that the real wedge, which is the entanglement wedge, can go inside, but it can't go all the way.
But at least the formulas you wrote down did go inside.
That's correct.
No, but we were trying to do, that was a very super gravity kind of analysis.
Yeah, so, the goal of this whole program is to go behind the horizon, right? Those methods don't quite, but, the claim here would be that no method can go arbitrarily far on the next slice.
So that's what I was trying to do.
Yeah.
I know it's good, but that's good.
Yeah, and so that's what it means to sort of lose the operators from the code subspace, is they sort of leave the regime of validity. And then, that's related to the idea of firewalls. So a firewall person would say that happens already at the horizon in a sufficiently generic microstate. But certainly that wouldn't follow from the discussion here. That requires to get all the factors right.
And what does it mean that there is no code subspace encoding such operators? What does it mean?
Yeah, I wouldn't say it that way. I would just say that there are operators which aren't really observables from the point of view of a bulk person, right? Who makes a black hole, and because these things away in the nice slice aren't things you can see, right? Like if you jump in here.
But what about a few local operators well behind the horizon?
But how far behind? So I wanted to make. Well, now we're getting into metaphysics, but so I would say that things that are accessible by someone who jumps in, say in this area, had better make sense, at least for that person.
Right.
But that one doesn't need to.
Fine. But that will be consistent with what you say, that things behind the horizon but not too far behind the horizon.
Yeah, that's right.
Will be reconstructed.
Yeah, that's right. But then how far and in which states, right? These are the questions which I don't always have the answers to. But it's also, we can also just say, okay, we have this subspace where there aren't black holes, and then this whole machinery of quantum error correction is going, and the observables keep us within that subspace. So then now we can ask, can we generalize them to observables on some larger subspace that includes the black holes, and that now becomes a very delicate question. And I don't want to claim I understand all of that. Already we have our hands full, I think, just understanding the case about the black holes. I just brought it up to emphasize how to think about this inequality.
So can this give some qualitative notion of the entropy of the black hole from how many inaccessible
I think that's kind of what we got out of this argument, right? So because remember, I didn't say anything about black holes when I derived this. Right? We looked at the CFT and we discretized it into these n squareds, right? These regions with the n squareds, and we saw that that's when the code subspace breaks. So that tells us that at least the power of n that is going to be n squared and not something else. Now, of course, in terms of deriving the coefficient, then we're going to need to first get local Lorentz invariant physics, right? So that just from these kind of general arguments, we're not going to get that.
You didn't say anything about finite temperature here, which is has different.
Well, I could say something
different.
about it. So I mean, so we could certainly, so the thermal AdS gas, we can certainly consider here. That's just a mixed state on the code subspace. So there's no problem with that. Yeah, now at sufficiently high temperature, then it's going to be dominated by states which, at least so far, aren't in the code subspace as I've defined it. Now, yeah, I mean, again, time is limited. I mean, I do know some things about how and when you can include black holes in the code subspace and so on, but this gets into the, let's first understand the simple version before we try to put on all the bells and whistles. Okay, so the next thing I was going to do, and we can discuss whether now it's good to do it now or do it next time, although, well, I guess.
Can I make a request? I'm sorry. Can we end by 1:30 today? Is that possible?
Yeah, so, right, so, but then I think it means we won't do it, but let me say what it is.
But you can stop. Yeah, sure. No, I was just saying.
We have 9 minutes, so, yeah. So let me just say the big picture, and then maybe the details we can discuss tomorrow. So far we have this, there's a general theory of quantum error correction, which I didn't really tell you about. The only thing we really explained was this Q-trip model. And then we saw that AdS CFT, continuum conformal field theory, apparently, the bulk tells us that it has to be an error correcting code to make sense of this AdS Riddler reconstruction. But it would be nice if there was something sort of halfway in between, right? Because the 3 Q-trip, it's nice, but it's kind of too trivial. It's so trivial, right? I mean, in particular, you don't have a volume's worth of degrees of freedom in the bulk. So these things like, being near the boundary is well protected and so on, you can't really see that in the 3 Q-trip model. And you also can't really probe this idea that going outside of the code subspace corresponds to black holes. So it would be nice to have a model which is more general than the 3 Q-trip model, but still simple enough to be exactly solvable, but which does have these features precisely. So you can see this radial direction, and you can see that the black holes work by sort of removing regions of space from boundary axes. So indeed, the tensor network models that people have been studying do precisely that. So the next thing I was going to do was explain the simplest one, which is the so-called happy model, where we can see, which is still exactly soluble, and we can see that it does all of these things. But okay, yeah. So that's probably like another 20. Well, given the speed that we go, let's say half an hour. So probably we should do it tomorrow. All right, and then eventually we want to get to the document. We'll see how much.
So Thursday, actually, we were just discussing actually that up to Tuesday, one more lecture can be given on Thursday.
We're on Wednesday.
Wednesday, I'm really sorry. It seems like I might have to travel Wednesday.
Okay, I mean I can go all day, all night. So.
But I mean, we can still have it. I'm sorry.
No, I mean Shiraz also is not here on Wednesday, so.
I'm not here on Thursday.
Yeah, but missing one is better than missing 2 people. So.
Thursday we can have additional.
So yeah, can we also try starting at 10:30 tomorrow?
Yeah.
Tomorrow.
Let's start at 10:30. We can ask.
The room is free.
Room is free. Then let's.
So it looks like Subrat is gone, but
Is Subrat there or no?
I think Subrat is not there, right?
Okay.
Sudeep, so we can ask. We can tell them at least.
Yeah, Subrat is not there. So how do you guys feel about doing 10:30 tomorrow morning?
Yeah, tomorrow at what time?
10:30.
Yeah, 10:30 is okay for us.
Okay, can you check also with Subrat and then tell us if it's not okay with him?
Yes, we can check that.
And this time we'll be more organized. So we promise that we mean it this time.
Yeah. I'll tell you what. Let's agree to start at 10:30.
Yeah.
I'll also talk to Subrat and personally request him. And I think he, of all people, if he's half an hour late, he will catch up. I mean,
Yeah,
that's the
that's
start.
true. That's true. Yeah.
Okay, so then 10:30 tomorrow.
Yeah.
Can we say that?
Yeah. But, questions from Bangalore?
Question from Mumbai. Can you give some references? It's very important.
Yeah. Okay. Let's see. Well, yeah. There's a bunch. Yeah, maybe it's better. Let me think how to do this. Okay. Actually, what I recommend. recommend, as far as references are concerned, is that, so there's a paper by me from last summer, which has Ryu Takanagi and quantum error correction in the title. And if you read the introduction of that, it has all the references and some discussion of the history. So that saves me from writing it. Now let me just say quickly verbally, in the interest of fairness and being honorable. So all of the stuff about solving bulk equations and so on goes back originally to Banks, Douglas, Horowitz, and Martinek, 1998. Yeah. So and the real idea there of solving the equation radially is from them. Then in terms of working it out for interactions and fields, gauge fields and so on, then Hamilton, Cabot, Lifshitz, and Loeb had a whole program going through the 2000s working out many details of this. So that's HKLL, which is the acronym most people use for this idea. Then the best explanation, which I did mention, is I think by Heemskerk, Kamarov, Polchinski, and Sully. That's 2012, HMPS. So they gave this discussion in terms of the space-like Green's functions, which I presented. So which is the only way to explain it in a lecture. So the way that Hamilton, Cabot, Lifshitz, and Loeb are thinking about it is they said we're going to construct operators that computed space-like separation, and then worked very hard to figure out how to do that. So as far as the back, right, then the AdS Rindler reconstruction also originally was worked out by Hamilton, Cabot, Lifshitz, and Loeb, and then there's a paper by Ian Morrison which explains the distribution of the smearing functions. Okay, as far as the puzzles that we were talking about, so the one about commuting with stuff in the center, what I think was in some sense discussed by Polchinski, Susskind, and Tumbas in around.
Because.
Yeah, in the precursor paper.
Oh, is that right? Yes.
Yeah. They didn't talk about the time slice axiom, but that was the issue they were confused about. And then the one about the 3 and the 2 and so on is from my paper with Ahmed, Almeri, and Shidong, which then is everything else I discussed today is also in that paper. So that's all. I guess that's the references up until now.
Sorry, I have one more question.
Yeah.
Since we have 2 minutes more.
Yeah.
What? Suppose I were interested in the firewall paradox.
Yeah.
What lesson should I draw about that from your story?
Well, the jury is still out on that in terms of details, but I think that one lesson already is that when you use bulk effective field theory to derive algebraic paradoxes, be careful, because this time slice axiom one, we could have written in the paper, here's the time slice axiom, here's the commutator for bulk physics. They're obviously inconsistent, and therefore bulk physics can't emerge.
But
right? We could have written that paper, and we didn't. And the firewall arguments so far are along those lines, right? I mean, there's never here's the theory of the firewall, and here's why it's true. It's just here's some things that bulk physics suggests should be true, but they seem to be inconsistent with the CFT.
But in more detail, if you could reliably reconstruct bulk operators well within the horizon, then you would claim a demonstration that there is no firewall line.
If I could do it in generic microstates, then yes, that's right. Right. So the firewall paradoxes are arguments that you can't do that.
Yeah, generic microstate. I mean, if you could do it for the average microstate which corresponds to the black hole geometry, right? The black hole geometry is not a particular. Maybe we get into this.
Oh, well, okay.
It's not a particular microstate.
This one I'll fight about all day.
Oh yeah.
Yeah.
Oh, you may say it's a typical microstate.
Yeah, typical microstate.
All right.
I would say a black hole is a thing, and even if you make it in a pure state, the geometry outside looks like Schwarzschild. Yeah, I've encountered people who say it doesn't, but I never understood this.
No, that's fine. That's fine.
But you do not yet have a clear view about whether you could do that.
No, I think the evidence. I mean, well, this will be my opinion, but I would say that if you look at the derivative over the last 2 years, it's going in the direction of being able to do it.
But yes, just at physics level, you do not feel you have clear
No, absolutely not.
sense.
No. If you ask me what's my Bayesian, how would I bet?
Yeah.
Yeah.
I probably 75% odds to not having firewalls, except non-generic cases where you put them there. But I don't really get to make that claim until I've pointed out what's wrong in the arguments that have been made for firewalls, and I'm not yet in a position to do that.
And you cannot, all the arguments made for firewalls cannot be circumvented using,
It's
you
not
cannot
clear.
point out.
It's not clear.
Flaws in all of
No,
it.
they could be. I mean, there are potential flaws in it. The problem is the arguments aren't vigorous. There's a bunch of hand waving involved, and there are a lot of details which aren't treated in the arguments. So that right. I mean, there's certainly. I think there's room for a solution along these lines to squeak through. Right. I mean, here. So what we saw here was that you couldn't get the bulk algebra on all the states, but you could get it on the states where it mattered. Right. And the issue with the firewall is to see it. It's harder to tell if that's really true. To know whether it's the states that matter, you have to understand the bulk physics quite well.
Let me even say, locality was an important ingredient in many of their paradoxes. Now, one of the big things that came out of, Susskind and Maldacena was that locality can sometimes fail in spectacular ways.
Right.
If you're willing to entertain that.
I think that's what we've already seen here too, right? Because we've seen that locality is not an operator equation in the CFT, right? That's what we learned here. It's something that's more subtle than that. And it's something that uses this non-local entanglement between the different things in the boundary. They're essential for getting locality in this direction to work. So locality is kind of, right, that was always the criticism of AMPS, is that they use bulk effective field theory to drive paradoxes, but we know bulk effective field theory is wrong. Right. They try to take things from bulk effective field theory and put them into the theory with the microstates, essentially without any modification or serious thought. Well, that's not fair, but I mean more not as much serious thought as probably is called for. Right, and we saw here also doing that gets us into trouble. And here we're able to resolve it. So I would hope that So I mean if we think about the interior, at a high enough level of sophistication, one of two things will happen. Either we'll see that there's no firewall and we'll construct these operators, or we'll discover the dynamics that make firewalls. And either of those are interesting, right? But until we do one of those two things, then the jury is still out. I don't think you can. It should be a calculation if we do. We shouldn't just sit around saying, "Oh, how do we feel about having firewalls?"
But it's not a calculation. It's not a calculation. Is it a calculation you can imagine doing a recoupling?
Oh, you mean a CFT?
Yes. Is it some?
I don't know. No, I don't know. At the moment, I don't even in principle know how to do it. It's not a question. Even if you gave me a computer that could kill n equals 4 super angles on coupling tomorrow,
Yeah.
I wouldn't know how to answer this question. So it's not a computing resources question. It's really a conceptual question.
It's true we don't know the question, but since we know this much from the bulk that you don't form the black holes in any sensible way at recoupling.
Or the black hole has string scale.
Yeah.
That's what I was at.
The question,
Oh.
even when we finally figure it out, will be tied to the fact that you have an interior and
We kind of need to answer it at strong coupling.
Yeah, so that's not a calculation you can really imagine. You want some. There's no realistic chance you do a calculation.
Oh no, but right. But the way these things work is once you know the question, then you won't need to do the calculation.
Right.
That's how we know.
Right.
Everything important. That's how it works. Maybe with the exception of the sign of the beta function in QCD.
Right. So
But even that is kind of the limit is obvious, right?
there should be a calculation that you can set up in a field theory that you can do at weak coupling, which gives you some answer. Then you can imagine extrapolating a strong coupling to something else.
Yeah, but I don't think. Yeah, so I think weak coupling in the CFT I think will not help. But we need other methods, right? For example, this came out of something that had nothing to do with weak coupling. So you can imagine some sufficiently refined version of that.
Everything generic comes out without saying strong coupling, but details will require something that's not true at weak coupling but is true at strong coupling will require strong.
Yeah. Well, right, yeah, I mean, some of the questions have been really well defined.